Alrighty, so we saw last lecture that there's this thing called the particle wave duality. Alright, it applies to light. And we saw that the energy of a light particle, a photon, is equal to h times the frequency of the photon. It's strange to think of particles having a frequency, but there it is. That's the energy of a photon, where h is Planck's constant, and it's a little number. Ten, 6.63 times 10 to the negative 34 joule seconds. Joules times seconds. And I also want to point out, I meant to say it, I think last video, is that this is often written as hc over lambda because frequency is equal to c over lambda. Right? Remember, lambda f equals c. So substituting in for frequency, c over lambda. So sometimes you see this written not in terms of frequency, but in terms of lambda. Again, lambda and f, wavelength and frequency, are interchangeable. You can describe light by its wavelength or by its frequency. They're equivalent to each other. If you list frequency, I can give you the wavelength. If you give me the wavelength, I can give you the frequency. So sometimes it's written this way. So there's this particle wave duality. Sometimes we do experiments, Young's double slit experiment, thin film interference, and the results only make sense in terms of light being a wave and force us to conclude, without any wiggle room, that light is a wave. These other two experiments, which I didn't talk about in detail, just for the sake of, we only have so much time, the photoelectric effect and the Compton effect, the results of those experiments force us with no wiggle room to conclude that light is a particle. So we have this weird thing, the particle wave duality, which sounds nice and spooky, right? But there it is. Applies to light. Well, French fellow Louis de Broglie. De Broglie, I guess the G is probably silent if you say it in French. I'm not going to attempt a French accent here. Us Anglos call him Louis de Broglie. Okay, so I'm going to say it that way. Came up with an idea in his PhD thesis back in 1921, maybe, something like that. He said, well, why does light get all the good spooky stuff? Why does light get to have this particle wave duality? Why just light? Why not matter? Why? Maybe matter has a wave nature, right? We think of matter like protons and electrons, neutrons, and all the other ons. And all the things that those ons make up, like molecules and cats and planets. You think of those as particles, right? You think of those as being solid particles. And when you imagine an electron, you probably imagine a super teeny tiny little ball. I do. Okay, usually. I mean, not half the time. Protons, neutrons, you think of, when I draw them on the board, I draw these little circles, right? And that's the electron. That's the proton. We think of them as being particles. You and I, we think of as being particles, right? When we meet each other, we bounce off. We don't go pass through each other like a couple of ghosts, right? We're not waves. We're particles. We bounce off each other like a couple of billiard balls, right? Maybe not, but still, we don't pass through one another. We are particles. But what Louis de Broglie said is maybe we are not just particles. Maybe the particle wave duality applies not just to light, but also to matter. Stuff with mass, like electrons, protons, other ons, cats, rain, everything. You and me, my glasses. Maybe the particle wave duality applies to those too. Maybe my glasses are both particles and waves. Okay, both a particle and a wave. Maybe this pin cap is not just a particle, but also a wave. Now, there seems to be no evidence for this, but de Broglie actually suggested something called the de Broglie wavelength, saying the wavelength of matter is equal to Planck's constant divided by mv. This is known as the de Broglie wavelength. De Broglie wavelength. And suggested that all matter has a wave nature. That everything, not just light, but also stuff, matter, has a wavelength, has a wave nature. Maybe I have a wave nature. Although I look solid, maybe I'm not. Maybe if you get up super close and look at the atoms and stuff in my skin, it wouldn't look so solid anymore. Maybe it would look kind of wavy. He was right, of course. Matter does have a wave nature. The Broglie wavelength is exactly right. Okay, so how can it be? Well, let's give an example here to figure this out. Suppose we have a baseball. Now, baseball season is, of course, postponed like nearly everything else in the universe these days. But a good fastball pitcher can pitch a baseball about 100 miles an hour. Okay, so let's imagine a baseball going 100 miles per hour. Now the mass of the baseball is about 145 grams. Okay. And we want to know what's the wavelength of the baseball. Now you think of a baseball as a particle. But what de Broglie is saying, and what I'm saying, is that the baseball has a wave nature, and it's got a wavelength. Just like light has a wavelength. The light we can see between 400 and 700 nanometers. But what's the wavelength of a baseball? Well, it depends on how fast it's going, it turns out. 100 mile per hour fastball, that's about 44.7, am I in there? Yeah, meters per second. So the de Broglie wavelength of a baseball moving 100 miles per hour is 6.63, right? It's just h over mv times 10 to the negative 34th joule seconds divided by 0.145 kilograms times 44.7 meters per second. Plug it in, see what you get. What you get is a really, really, really dang small number. 1.0 times 10 to the negative 34th meters. That's the wavelength of a baseball. Well, no wonder we didn't know it was there. That is trillions upon trillions of times smaller than we could ever measure. 10 to the negative 34th meters is way below what we could even in principle measure. Quantum effects keep us from measuring it. Okay, we just can't measure it. So you and I are never going to notice or be affected by the wave nature of a baseball. And the same thing applies to you and me. Right? Our masses, our speeds might be lower, but our masses will be a lot bigger. Our wavelengths come out to be about the same. My wavelength, your wavelength. Okay, our de Broglie wavelengths are very short, way short. But if we have a 100 mile per hour electron, then the de Broglie wavelength comes out to be about 16 micrometers. This is just, 1%. It's 1.6% of a millimeter, the small separation on a meter stick. This we can measure. Okay, a micrometer, we can measure things way smaller than a micrometer. Okay, we can get a million times smaller than that. We can measure things maybe even 1 trillion times smaller than that. But still, that's nowhere near the wavelength, the smallest wavelength of baseball. So for an electron, put in the mass of the electron, 100 miles per hour, you get this is measurable. This is something that we could get in the lab and measure. This wavelength of a baseball is not measurable. I don't need to tell you, you already know the answer, which is that we have looked to see if matter has a wave nature, and it does. Electrons interfere. You know, interference, the thing that tells you the thing is a wave. We can have electrons interfere with each other. The same way that light particles interfere with each other. Young's double slit experiment for electrons. Instead of passing light through a couple of slits, we pass electrons through a couple of slits. And we get interference. So, the particle wave duality applies to light, and it applies to matter. And this is the wavelength of a matter wave, or a de Broglie wave. Okay, depends on Planck's constant, and the mass of the particle, and its speed. More coming up. Stay tuned.